After perhaps the photon, no subatomic particle is more instrumental in our modern way of life than the electron. Considered elementary particles, electrons flow through our devices like blood through our veins, giving them life so that they may serve us. But what do electrons look like? Why do they behave as they do? How are they related to their sibling leptons, the muon and the tau? Stay tuned to explore answers to these questions in The Nature of Leptons. In part 1 of this series, results from electron-proton deep inelastic scattering done at the Stanford Linear Accelerator Center, SLAC, in the late 1960s, combined with scattering data from the Jefferson Lab, JLab around the year 2000, show that the proton is made of 9 particles that appear to be muons. Part 2 of this series showed that deep inelastic scattering done at the Hadron Electron Ring Accelerator, HERA, showed those muons are made of electrons and positrons. However, the electrons and positrons making up the muons and the proton, labeled beta electrons and beta positrons, are slightly different than the free electrons and the free positrons commonly seen in nature. Free electrons appear to be the beta electrons found in the muon, coupled with electron neutrinos, and free positrons are the beta positrons found inside the muon, coupled with electron antineutrinos. So a question becomes, how do the beta electron and the neutrino configure themselves to form the free electron? A scenario where one of the particles orbits the other in the free electron could produce a working model. Typically in two-body systems, the lighter body orbits the heavier body, for example, like the moon orbits the Earth. But in that situation, the force between the two bodies, gravity, is driving the dynamics of the system. The free electron situation appears to be different. The beta electron appears to be the orbiting particle, with the neutrino at the center of the system. It appears some unknown force is causing the electron to orbit the neutrino. Paul Dirac postulated in his 1933 Nobel lecture that
it is found that an electron, which seems to be moving slowly, must actually have a very high-frequency oscillatory motion of small amplitude superposed on the regular motion which appears to us.
The high-frequency oscillatory motion Dirac spoke of may be the beta electron looping in a tight orbit about a central neutrino as the pair moves through space. Assuming that the orbit precesses quickly over time, the beta electron may enclose its companion neutrino inside a virtual hollow sphere formed by the high-speed precession. The free electron magnetic moment seems to support this scenario. The measured free electron magnetic moment, mu sub e, is slightly greater than the Bohr magneton, mu sub b, which is considered an approximation of free electron magnetic moment. The electron magnetic moment is 1.00116 times the Bohr magneton, where 0.00116 is the electron anomalous magnetic moment. The difference is small, but there is a difference, and that difference provides the clue needed to decipher the structure of the electron. The dimensions of the magnetic moment, mu, typically expressed as joules per Tesla, can be reduced down to coulombs meters squared per second. This makes the magnetic moment look like the product of a moment of charge, coulombs meters squared, and a frequency, reciprocal seconds, with the moment of charge being the charge equivalent of the moment of inertia for mass, kilograms meters squared. Therefore, the magnetic moment of a charged particle can be expressed as the moment of charge of the particle times some rotational frequency associated with it. The moment of inertia or moment of mass, I, for a solid sphere, is I equals 2/5 mr squared, where m is the mass of the sphere and r its radius, and for a hollow sphere, I equals 2/3 mr squared. This means the moment of charge for a solid sphere should be I equals 2/5 qr squared, where q is the charge of the sphere, and for a hollow sphere, I equals 2/3 qr squared. In the case of the free electron, Its classical radius is roughly 3 times the radius of the proton, but the true free electron radius is likely not that large. If the radius of the free electron is about the same as the muon radius in the proton, it is about 1/3 the proton radius, but 1,836 times less massive than the proton. Assuming the matter forming the free electron is the same as that forming the proton, for the free electron to be 1/3 the proton radius, and the matter forming it retain the proton's density, it must be inflated like a balloon, forming a thin-shelled hollow sphere. This would make the free electron's moment of charge, I sub e, 2/3 the electron's charge times its radius squared, which here is assumed to correspond to its magnetic moment, being the Bohr magneton. However, if the free electron is actually a small, charged particle in a high-speed orbit about some central entity like the neutrino, then the precession of its orbital plane about an axis of revolution through the central entity would make the electron scribe out a virtual thin-shelled hollow sphere. The moment of charge of the orbiting particle is slightly greater than that of a static hollow sphere. This is why the Bohr magneton so nearly matches the free electron's actual magnetic moment. The moment of charge of a thin-shelled hollow sphere approximates the moment of charge of the free electron's orbiting particle. Now, the moment of charge of the free electron has two components: the moment of charge due to the particle's orbit spinning about an axis and that of the particle itself. In order to determine the total moment of charge of the free electron, a calculation known as the parallel axis theorem must be used. Briefly, the parallel axis theorem for charge states that the moment of charge of a body with respect to an axis not through the body, I prime, is equal to the moment of charge of the body, I, plus the product of the charge of the body, Q, and the average distance squared, d bar squared. The body is from the desired axis, or I prime equals I plus Q times d bar squared. If the beta electron forming the free electron is a solid spherical particle, then its moment of charge, I sub beta, would be 2/5 times the charge of the beta, times the radius of the beta, squared. Assuming, for simplicity, that the orbit of the beta electron is circular, its average distance squared from the moment axis during a complete orbit is 2/3 times the radius of the orbit, squared. This makes the QD bar squared adjustment to the beta electron magnetic moment 2/3 times the charge of the beta times the radius of the electron squared, which is equal to the hollow sphere moment of charge assumed in the Bohr magneton. Now, the total moment of charge of the free electron becomes 2/5 times the charge of the beta times the radius of the beta squared plus 2/3 times the charge of the beta times the radius of the electron squared, or 1 plus 3/5 times the beta radius squared, divided by the electron radius squared, all multiplied by 2/3 the charge of the beta, times the electron radius squared. Note that, in the expression for the total moment of charge of the free electron, the term 1 plus 3/5 times r sub beta squared divided by r sub e squared modifies the moment of charge of the Bohr magneton, just as the anomalous magnetic moment modifies the Bohr magneton to produce the electron magnetic moment. If the two represent the same adjustment, then 1 plus 3/5 times r sub beta squared divided by r sub e squared equals 1.00116, so that 3/5 r sub beta squared divided by r sub e squared equals 0.00116, and r sub e, the radius of the electron, equals 22.74 times r sub beta, the radius of the beta particle. The radius of the free electron is nearly 23 times that of a beta electron. If the free electron radius is the same as the muon in the proton, 0.31 times 10 to the minus 15 meters, then the radius of the beta electron becomes 1.36 times 10 to the minus 17 meters. So, a model of the free electron becomes a beta electron orbiting a central electron neutrino with a radius 23 times its radius, where the orbital plane spins about an axis through the neutrino. The free positron is a similar setup, except it is a beta positron orbiting an electron antineutrino. Muons are often called heavy electrons because, other than their greater mass, they often behave like electrons do in subatomic situations. The muons inside the proton appear to be made of 204 beta electrons and positrons on average, but the free muon is 207 beta particles, 104 beta electrons, and 103 beta positrons. The difference is likely due to the muons inside the proton binding together by sharing 2 or 3 beta electrons and beta positrons, similar to how atoms share orbital electrons to bond together. When a muon decays, it disintegrates into a free electron, an electron antineutrino, and a muon neutrino. Since the free electron contains an electron neutrino, it appears an electron-neutrino antineutrino pair is produced during the muon decay. The 103 beta positrons in the muon eventually annihilate 103 of the beta electrons in the muon, spawning a neutrino-antineutrino pair. The neutrino couples with the lone beta electron remaining after the annihilation event to form a free electron. However, only a muon neutrino appears during the decay, with no sign of a muon antineutrino involved. This suggests that the muon neutrino was part of the muon before the decay, and not formed by pair production during the decay. The muon neutrino is apparently kicked out of the muon during the annihilation event. The free muon containing a muon neutrino is similar to the free electron, which has one of its neutrinos as part of it. A central neutrino is apparently a characteristic of lepton structure. A potential problem with forming a muon model containing both beta electrons and beta positrons is that they are antiparticles that might be expected to instantly annihilate each other. Instead, the muon decays with a 1.56 times 10 to the minus 6 second observed half-life, a virtual eternity in subatomic space. The Hera deep inelastic scattering data provides a reason why the muon can exist containing the antiparticles. The muon F2 curve has a sharp peak with an F2 value near F2 equals 1. This indicates that the particles forming the muon do not interact strongly with each other. Rather than binding together like protons and neutrons in the nucleus of an atom, the particles likely reside in orbitals, like the electrons in atoms. As a result, the beta electrons and beta positrons making up the muon are not in contact with each other while the muon exists, and no mass annihilation occurs, at least not until the muon decays. Like the free electron, the free muon has a magnetic moment that is slightly greater than what might be termed the muon magneton. Its charge times Planck's constant, divided by the quantity 4 pi times its mass. Because the muon and the electron have the same charge, the muon and Bohr magnetons differ by only the ratio of electron mass to the muon mass. Consequently, the muon has an anomalous magnetic moment that is nearly the same as the electron anomalous magnetic moment, 0.0011659, compared to the electron's 0.0011596. Since the free electron anomalous magnetic moment is tied to the ratio of the beta electron radius to the free electron radius, the two anomalous magnetic moments being essentially the same, suggests that the free muon radius is about the same as the free electron radius. If, as with the electron, the free muon anomalous magnetic moment is equal to 3/5 times the beta electron radius squared, divided by the radius of the muon squared, then the muon radius becomes 22.65 times the radius of the beta particle. With the free electron radius being 22.74 times the beta electron radius, a muon radius of 22.65 times the beta electron radius indicates that the leptons appear to have a standard radius, 22.7 times the radius of the beta particle. With that, trying to stuff 207 beta particles in orbits the size of the beta orbit of the electron and maintain this muon size does present a challenge. A muon with a radius that is 22.65 times the radius of a beta particle has a circumference of about 142 times the radius of a beta particle at the muon equator. Each beta particle has to pass through the equator of the muon twice during an orbit, and they are 2 beta radii wide, so each beta uses 4 beta radii of the equator circumference. If the 207 betas forming the muon are in individual orbits, the muon circumference would need to be 207 times 4 beta radii, or 828 beta radii. This would require a muon radius of about 130 times the radius of a beta particle. Fitting the 207 beta particles in a muon with a radius that is 22.65 times the radius of a beta particle appears to pose a problem. One way to remedy this problem is to place multiple beta particles in each muon orbital. Since the muon radius is about 23 times the beta particle radius, dividing 23 into 130 should indicate the number of beta particles each orbital must contain to make the muon model work. The result of the division is 5.7, which rounds up to 6. If each muon orbital holds 6 beta particles, presumably 3 beta electrons and 3 beta positrons, alternating, a muon with a radius 23 times that of a beta particle, containing 207 beta particles, can be made. If each muon orbital can hold up to 6 beta particles, the 207 beta particles of the free muon would require 34 orbitals, accommodating 204 of the betas, and a 35th orbital that has only 3 beta particles in it. So, the free muon model becomes a central muon neutrino, surrounded by 35 orbitals precessing about an axis through it, 34 containing 3 beta positrons and 3 beta electrons, alternating, and 1 containing the remaining 2 beta electrons and 1 beta positron, for a total of 104 beta electrons and 103 beta positrons. Because the 34 orbitals with 3 beta electrons and 3 beta positrons have a net charge of 0, they contribute nothing to the moment of charge of the muon. Only the orbital with the 2 beta electrons and 1 beta positron, giving it a net charge of -1, produces a moment of charge that is essentially the same as the free electron moment of charge. However, the additional mass of the free muon reduces the frequency of the muon relative to the electron, causing its magnetic moment to be smaller by the ratio of the masses. Unfortunately for the muon, the orbital with only 3 beta particles, that gives it a magnetic moment, also leads to its ultimate demise. The charge imbalance of the orbital apparently causes the lone beta positron in the orbital to eventually annihilate one of the 2 beta electrons in the orbital, creating what is likely the future electron orbital and setting off the annihilation event that turns the muon into an electron. Based on the structures of the free electron and free muon determined here, leptons appear to be beta electrons and beta positrons in precessing orbits about a central neutrino at a radius of about 22.7 times the radius of the beta particles. It also appears that the free electron is essentially the remnant of the free muon after the muon's annihilation event occurs. The next video takes a look at the final big lepton, the tau, and explores how what looks like a tau may not always be a tau. It also shows how, when not considered fundamental, leptons have a genealogy that links them to other classes of subatomic particles and reveals once again how particle physics has failed.